Good afternoon, everyone. I'm really excited to be invited here. Thank you very much for inviting me. And I came to share with you a little bit about my own personal experience, but a little bit about also the department in terms of numbers, our future vision, what we've done in the past, and what we will be doing, and impacting not only the security, but also the technological superiority and the sustainability of the state of Israel, as well as the world as a whole. So I'll tell you guys a little bit about my story first. I was born in Izmir, Turkey. For those of you that may not know where that is, it's actually relatively close to Israel. So this is Israel, this is Turkey right here, and this is Izmir. So those of you that might have taken cruises, you probably have come to Ephesus, right? And Ephesus is just in the periphery of the city of Izmir. It's a beautiful city. So when I was 17 years old, I was very passionate about science. And I was lucky to have parents that were really enabling that and encouraging that. And they agreed to send me to Purdue. So I got all my degrees at Purdue University. So some of you might ask, why Purdue? Well, I was relatively hyperactive. And my parents wanted to make sure that I get a good education, but at the same time that I'm relatively safe. And you know, it's Midwest. With that said, actually, like our speaker yesterday, I loved my time in the Midwest. I made some of my best friendships. And to this day, we are in really close touch with all my friends from the college years. So I got my bachelor's, master's, and PhD there. And then afterwards, I spent some time in the Von Karman Institute for Fluid Dynamics in Belgium. It's a NATO-funded research institute that is established to promote academic research in dual-use technologies. So dual-use meaning both military and civilian use, right? And growing up in Izmir, in an extremely Zionist family, it was really my dream to be a faculty member in Technion, believe it or not. And for me, you know, the moral of the story is be careful what you wish for, it might actually come true. And it's 100% true. That was really my dream. And I was at the time 28 years old, just finishing my PhD and a bit of experience in Von Karman Institute. And I got recruited to Technion, and the rest is history. I was at the time the youngest faculty member in Israel, and now not anymore. I came in and joined the elite club of faculty members of Technion in 2012. In the beginning, I came in as a lecturer. I've been there for about 11 years. I came in as a lecturer, and then assistant professor, and associate professor, and I'm just going through the grinder. So what I want to talk a little bit about is the aerospace engineering department, which I am a part of, and I've been a part of for the last 11 years. This department is located, so I want to take a picture for you guys in order to relate where it is geographically. So we're located at the very southern tip of Technion, overlooking the entire beautiful Haifa Bay Area. And these buildings that you see here constitute the department itself. And this is the historic building that was the very first building on this campus that was built in 1954, right here. And these are some of the laboratory buildings that are supporting it. So Israel's only aerospace engineering department, as you can imagine, is quite important. It fills a large and important void. Oops, now I'm getting an echo. Maybe I'll leave this here. It fills a large important void in the national security needs, but also technological needs. So, and the aerospace department itself, it actually does a quite well job doing it. So we are actually the 22nd, we have a ranking, you know, there's these conventional rankings for all these things. We are ranked 22nd in the world in the discipline of aerospace engineering. This is the department that's highest ranked in Technion among any of the disciplines. So clearly we do a reasonable job doing our jobs. So I wanted to kind of give you a background about the department in numbers so that you can actually, you know, get a feel for it. So we are around 30 primary investigators or principal investigators. So there are 30 roughly faculty members. And we span a very broad range of disciplines. So we have folks that deal with guidance, navigation, and control. These are the people that deal with autonomous movement of cars or missiles or UAVs. They're all the same technologies, right? Planning their paths and all that. We have people that are dealing with fluid mechanics, aerodynamics, and acoustics. And then we have a separate group of people that deal with structures and design. So these are the folks that actually look at if the part will fail or not and how to be able to make light structures that can actually fly, such as composites, right? And then we have folks, including myself, that deal with combustion and propulsion. So we are the guys that make engines fly, basic planes fly, right? We are the guys that deal with engines, whether they are for low-speed applications or all the way to the hypersonic regime. And then there's a fifth group of guys that deal with space. That's why it's Aerospace, right? And they would deal with astronautics. So among these 30 faculty members, we are really privileged to have a relatively young and dynamic body. Among them, almost 15 of them are relatively junior faculty members. So when I mean junior, in Technion, all of us, we come with an expiration date. Because it's true, there's a forced retirement age for any faculty member, right? So in our department, almost 15 of them have another 30 years on the clock. So it's relatively young. And among them, myself included once again, 8 of them are not inbred, meaning we come from scientific backgrounds that are not necessarily that previously existed in the framework of Technion, which is something very special because then you actually, instead of doing brain drain, you're doing technology transfer from places that you have actually been before, right? I want to talk about a bit the impact of some of the faculty members that we have in the department now and how that has actually influenced the state of Israel. So historically speaking, we had already 3 Israeli Defense Prize winners. Israel Defense Prize is a prize that's awarded by the President of Israel for significant contributions of the individual to the defense of the state of Israel. So we had 3 faculty members that had already done that, and we have 3 current faculty members that have actually received this prize just recently. So you can see some of the names there. In addition to the Israel Defense Prize, we have individuals that have made major contributions to the ballistic missile defense system. And what ballistic missile defense system is basically is Arrow 2, Arrow 3, Davis Link, and the one that you really know well is Iron Dome, right? So collectively, they're called the ballistic missile defense system. And it's called the most effective missile shield the world has ever seen by the Time magazine in 2012. So we have 4 individuals that have contributed to that. And in addition to that, there is OFEC 1, which has given Israel the space launch capability of satellites in the year 1988. And distinguished Professor Danny Weiss was heavily involved in that, and as an outcome of that, that's how the Asher Space Research Institute was founded. So these are really important contributions that the faculty members have directly done to the security of the state of Israel. And you see, kind of interesting, I picked these particular examples. There are many others. The reason that I picked these particular examples, because they cover land, air, and space. So all 3 areas that our department operates in. In addition to this, I will show you in our faculty vision, we're also trying to actually address needs of the sea in underwater vehicles. And I'll talk a little bit about that later. So in terms of the educational structure, our undergraduate student body is around 350 students. So it's not a small department, it's not a very large department, we're somewhere in the middle. Almost 40% of them are academic reserve cadets. That means these are individuals that come, get educated, and then go, such as Neta, right, later on to serve in the Israeli Defense Forces. So it's quite an important task that the department fulfills. In addition to it, recently, our basically diversification of the student body has been quite dramatic. In the last 2 years, we have almost 30% female enrollment in the department. So this is something really positive in the aerospace engineering department. So in addition to the undergrads, of course, we have graduate students. We have around 150 at any given time, and roughly 50 of them are international. And these people come from Germany, from Switzerland, from US, from England, from countries where they have already aerospace engineering industry, but they come on over because they really believe that our department has something to offer to them. So once graduating, our alumni occupy truly leadership positions in Israel's aerospace and defense industries. But more recently, because the skill sets that are acquired by all these students is so diverse, we started to fulfill the need of engineers in the startup industry. So some of our graduates, they don't actually go to the typical national defense industries, but they also are the powerhouse behind the growth in startups. They go to Mobileye, they go to Redis, they go to all these companies that build technologies for civilian use. They go to Siemens. So I tried to actually compile a number of different names. I'm not going to go over all of them, that our alumni has actually taken in the last number of years. So some of these alumni, they went into government positions, some of them went into the defense industry, and some others have gone into the civilian sector. So in the government, we had actually directors of the Israel's Missile Defense Organization, actually a number of them, and these are individuals that are truly in charge of developing, deploying, and operating all of the missile solutions of the State of Israel. In addition to this, as you can see, we had the director of Sorek Nuclear Research Center, also as one of our alumni. And of course, we had a number of generals in the Israeli Air Force that have actually come through, typically through our Atudei program, the Academic Reserve Cadet program. And lastly, of course, not only in the field of defense, but also in Ministry of Science and Technology, the CEO of the ministry is also one of our alums. As you can see, the skill set that our department offers to these individuals are really valuable for the State of Israel. So in addition to the governmental positions, we have individuals, as expected, as you would expect, that are in high up places in all the defense needs of the State of Israel. So if you look at actually Israeli aircraft industries and Rafael, and as well as Albit, a bulk majority of the individuals that fill the true leadership positions are all our department's graduates. So the head of the, Professor Sivan was mentioning the LAVI program. LAVI program was the challenge of the State of Israel to build the fighter jet. And the head of the LAVI program expectedly was one of our graduates. He later on went on to become the chief engineer of the Aero 3, which is in the Missile Defense Organization, right? And he later on became the chairman of Urban Aeronautics, another UAV-related company, right? So this is actually really important contributions. And in addition to the defense-related applications, we have also a lot of civilian-related applications that our alumni have contributed to, such as the Gulfstream. And Gulfstream is truly built by the IAI, Israeli Aircraft Industries. So in addition to this, of course, also in Rafael, we have a number of different individuals that have actually come to prominent places. So putting all this defense-related applications aside, let's talk a little bit about also the civilian sector. So if you actually look at it, today, majority of the electricity of the State of Israel comes from gas turbines. And most of them are actually built by Siemens. If you look at it, the CEO of Siemens Israel is also one of our graduates because we are the only body that actually gives education in the field of gas turbines. And we have individuals that have become the VP of engineering in El Al, and more recently, we're talking about the success of the Israeli space program and Bereshit and Space IL, right? About the moon landing mission. If you look at it, the top 3 individuals in Space IL which is the CEO, the head of the lunar landing program, and the controls engineer, which is just a controls mission. They were all of our alumni. So as you can see, we really value this industry-academia partnership, and we try to integrate it already within the body of the department. So in order to do that, Technion has created a new tool. This new tool is called the Research Fellows Program. So right now, in the department, just like us as academics, there are industrial people, industrial experts, that are actually coming and joining and teaching the students as if they are faculty members and sharing their experience and trying to actually bring a more applied perspective to the department. And this is happening not only with the traditional industries such as Israeli aerospace industry, but here at the end you can see that we have 2 faculty members from PTC and Mobileye, which are from the non-traditional fields. PTC is a computer, it's a CAD software, computer-aided design software, right? And Mobileye is all about these autonomous vehicles. So in addition to this, of course, the industry supports our undergraduate final year projects supervised by the industry. So all of our students in the 4th year, they come in, they need to do a design challenge, and this is 100% supported and supervised by the industry itself. So then that means they're doing relevant things for the future needs of the state of Israel. And in addition to this, we have a special program that's called Gvaim, which means heights. So we were discussing during lunch with Professor Uri Sivan about how to address the challenge of being able to educate a broad student body, but to be also able to feed the best knowledge to the top 1%. And this Gvaim program is targeting exactly that, is to be able to have an accelerated education for the top 1% of the student body that will later on, they will go and become academic, industrial, and basically leaders in the state of Israel. And this is also another program that's actually launched with support of all the traditional defense industries in Israel, IAI, Albit, and Rafael. So of course, with all this knowledge, we do a lot of outreach activities, we organize conferences. This year I had the privilege of basically being the program chair for the Israeli Annual Conference on Aerospace Sciences. We had over 550 attendants and 130 lectures. And this activity actually attracts not only the national players, but also international players. So this year, Lockheed Martin had a significant presence in the activity. So in addition to this, I also organize, actually this is an organization that I've been doing for the last decade, an annual Israeli symposium on jet engines. Our lab, I'll try to introduce you a little bit later, is the only academic body in the state of Israel that deals with gas turbines for propulsion and power generation applications. And we organize a symposium every year, which is a 2-day event with 200 plus participants. It's extremely international. We have people that come over from Germany, from Finland, as you can see, as well as Belgium, routinely. So in addition to this, I also want to talk a little bit about community engagement. So it's really important for us as Technion to be able to reach out to the high school students. So what our department does every year, it organizes 5+ visits from high schools all around the country, attracting 200+ students and trying to bring them and get them passionate about the aerospace field itself. To support all this activity, we have 5 research labs. So it's actually distributed across the different disciplines. So we have wind and water tunnel labs, flight controls labs, propulsion labs, which I am a part of, structures labs, and space labs. So this is actually an important slide. All these research labs, so there's Technion, and then there's TRDF, right? TRDF is a body that supports all the research activity within Technion, but it's a separate area. So as principal investigators, in order to fund our research activity, what we need to do is apply for grants. So none of the money that's donated to the educational body of Technion goes on to support research. It's our responsibility as individuals to raise that sum. So in our department, I tried to actually do a breakdown of roughly who funds the research activity in our department in order to promote all these activities. So in the private sector, we have all the usual players, which is Rafael, Israeli Aircraft Industries, Elbit, Manoa Bet Shemesh, which is the engine company of the State of Israel, but also some of the non-traditional players, which is Hyundai and General Motors, right? And at the same time, we also get significant funding from the Israeli public sector, which includes, of course, Ministry of Defense, but not only. If you actually look at it, we get funding from Israeli Ministry of Science and Technology, Ministry of Energy, Science Foundation, as well as international bodies. So if you look at that, international bodies, some of them are, again, defense-related, so such as US Air Force, US Navy, US Army, from which I actually also have the privilege to have grants from all three of them, but also from civilian bodies, because what we do is not only dictated towards the state of Israel's security, but also technological superiority. So you can see the prestigious Minerva Foundation, which is governed by Max Planck Society in Germany. They are actually funding some activity. We have some individuals that have received ERC, which is the most prestigious grant you can get in Europe, and German-Israeli Foundation. So this is basically mostly the past. So what I want to talk about a little bit about the future. The aerospace engineering is at a moment of transformation. Until now, a lot of the activity that was conducted, it was disciplinary. All those disciplines that I mentioned in the beginning, GNC, aerodynamics, propulsion guys and all that, nobody talked to one another as much. And that's why the impact that people could reach was relatively limited. But we truly believe the future challenges and the emerging technologies are inherently multidisciplinary. So what we are doing is we are building the department in a way where all these disciplinary fields are interacting towards common purpose to be able to identify and solve the future problems of Israel, as well as globally. So what are these basically research priorities that we have identified? Is autonomous aviation and future aircraft design, microsatellites, high-speed air vehicles, or you can also call it hypersonics, underwater platforms, and high-efficiency energy systems. So here I want to take a break. What I want to say is all of these have very obvious defense implications, right? The moment that we see that and we hear aerospace, we say, it's going to help and protect the people and all that. And it's 100% true. Our department is very important for the defense establishment of the State of Israel. But a lot of the technologies that we develop are also transitioned to the civilian sector. And the example that I want to give about this is about the invention of microwave. So some of you may know the idea that microwaves can be used for heating things, right? It was invented in 1945. It was a Raytheon engineer named Percy Spencer, and he was a radar operator in Raytheon, and because he was working late hours, he was actually stuck in his pocket with a candy bar. So one day doing an experiment, he notices that the candy bar is getting soft as a radar operator, right? And then he realized, he does a correlation that the reason that the candy bar is getting soft is because of the microwaves that are being emanating from the radar itself. And nowadays, we don't relate microwave to defense establishment and all that. It's a common household item. And what I'll try to convey to you is that some of these applications that we are focusing on for the future will also have direct civilian impact to all of our lives. So these are the emerging technology areas that we have identified that will touch all of our lives. One of them is drone swarms. So until now, right, we don't have corporate work of many aircraft. Typically, only recently we have started looking into how multiple aircraft can work together to fulfill a mission. So what we have identified as a future is that we will have multiple aircraft working together to fulfill this mission. And F-35 is a perfect example of that even manned aircraft. So F-35 today, it actually connects to multiple different aircraft as well as the base station, and all this information is propagated among all the players that are actually flying. Is something really marvelous. And we believe that this will also happen in autonomous drones. And we believe that the future aircraft will look nothing like today's aircraft. So you can see here on the right-hand side a depiction of what we believe some of the civilian transport aircraft will look like. And what is the enabling technology here? It's everything. It's the fact that it's multidisciplinary. Now we can actually promote manufacturing technologies that we couldn't do before, such as 3D printing and additive manufacturing. And Technion has a well-established center to address exactly that. There's very interesting and difficult controls challenges. So how do you actually control these surfaces in order to pitch and yaw your aircraft, right? That's also a big challenge. And now Technion has established multi-departmental controls people that are embedded there. And of course, structures. So fluid structure interaction, how the air going through the wing of the aircraft interacts with the body itself. And all of these together, besides the defense implications, we believe that will have a significant civilian impact in transportation, logistics, and monitoring, as well as sustainability. I mean, the target for the defense industry and the civilian industry is exactly the same. We want to be able to fly for as long as possible with a given amount of fuel in the wings of the plane, right? So energy efficiency of both the body as well as the propulsion platform, which is the jet engine, is very important. And we hope to address all of those challenges. On the space side, so this is all in the aero side, on the space side, we believe that the future will be mostly dominated by microsatellites. So until now, we had these big satellites that actually are fulfilling one particular mission. And in the future, we believe that there will be a swarm or constellation of satellites. And this future is already becoming a reality today. So if you look up in the sky, you can actually sometimes see these Starlink satellites that are passing by. So I actually live in Nakhsholim. It's right on the beach. And one night we were taking a walk with my wife, and it's pitch dark everywhere. And as we're walking by, we look up, and we see 5, 6 satellites that are actually flying in constellation. And it was the scariest thing, because at the time when you're looking at it, it looks like a UFO landing. So everywhere across Israel, there were UFO reportings, because everyone was convinced we are being taken over by the aliens. So this Starlink is only a starting point of the future. This will be the space-related applications in the future, and our department has already started working on this. Not only has contributed to Bereshit, the Israeli indigenous lunar lander, right? But also, we have actually continued supporting the Technion satellites, so such as the Samsung program. This was an activity led by Professor Beni Cukurel. He sent to space 3 satellites that were actually working together in order to fulfill a joint mission. So the challenge here is, how do you get 3 different bodies to work together autonomously? So in addition to this, of course, planetary landing system is very important, and we believe that the civilian impact of this, beyond the spy satellites, right, is going to be communications and space exploration. And Israel is becoming a part of this elite club of nations that is capable of doing that. So then that brought us to yet another thrust area, as we would like to call it, is hypersonics. So now there's a lot of buzz about hypersonics and high-speed air vehicles. And there's very obvious defense implications of that, is because you don't actually have to send a trajectory almost all the way to space and bring it down to your target, right? And you can actually fly this platform very close to the surface of the Earth, such that it's very difficult for your adversary to intercept it. But in terms of commercial applications, imagine going from New York to London in 1 hour. And Boeing actually has looked into that since, when I was in college in early 2000s, very early 2000s, this was actually one of the sales points of Boeing. This was actually the plan that they actually started. And one of the major challenges associated with this is the fact that this particular area is a very multidisciplinary problem. So some of the scientists that I know in Air Force Research Laboratory, they make a joke. They say, hypersonics is the future and always will be. The reason for it is very obvious. So when you're actually doing a design, you need to think about a number of different things. About aerodynamics, how the body is shaped, right? You need to think about structures, materials, right? Controls, both in terms of flight planning, as well as the actual change in the guidance program of this body. And Professor Risivan mentioned a few of them. And then that's just the external part of the vehicle. Now, something needs to make this thing fly, right? And that's the engine. So these things are equipped with a scramjet engine, which is a supersonic combustion engine. So that means the combustion takes place at a speed, just the combustion itself. The vehicle is flying 5 times the speed of sound. But even the combustion, the burning process, takes place a few times the speed of sound. So you can imagine how complicated it is to be able to design these things that have a direct correlation of different disciplines, and you cannot just optimize the problem just for aerodynamics and get away with it, and you can't just optimize the problem for structures and get away with it, and you need to consider all of those things together. So it's truly multidisciplinary. And the way that we're trying to address that challenge in Technion is in a truly multidisciplinary sense. And the hypersonic center that we are building is not equipped with only individuals from our department as the aerospace department, but also from material science, from mechanical engineering, from electrical engineering, is truly interdisciplinary, which is great. That's the way to address the future challenges of aerospace engineering. So now, one of the other research areas that we've identified as a department, as an emerging technology, is underwater vehicles. So all of you might say, well, okay, aerospace, so you address the land, the air, the space. What's going on with underwater? Isn't that a stretch? So if you think about it, water is just a sea of H2O, right? It's just sea of water. But where we live in is just a sea of nitrogen. That's all air is. We are just living and breathing essentially a sea of nitrogen. And a lot of the fundamental issues that has been addressed in the aerospace field, aeronautics field, in the last 150 years, they directly translate to underwater vehicles as well. And all the non-dimensional parameters and all the hard science that has been done, it also directly translates to underwater vehicles. And we want to leverage that. So why is this, one could ask, why is this important for the state of Israel? Well, nowadays, the assets in sea are much more important for the state of Israel than it has ever been. So if you look at it, as you're very well aware, Israel is no longer an importer of oil and gas. In the Levant Basin, we have actually created our own exploration and actually production of gas and oil. And this is a direct application of some of the technologies that we want to develop. So the last thing that I want to say in terms of our future thrust areas is high efficiency energy systems. So This directly targets sustainability. So we want to be able to make future engines that not only can fly very efficiently at low speed, but also at very high speeds. And this is actually very difficult. In addition to that, today's engines, they just use fuels that burn carbon. As you know, this is a big challenge, right? So in our department, we are now also conducting research in carbon-free fuels, such as burning ammonia as a hydrogen carrier. In addition to that, of course, distributed energy systems are important. We believe that the future aircraft will not actually have individual engines that are centralized, but distributed across the plane itself. And some of the lessons learned in this are not only applicable to aviation, but also to smart grids. So who will address all of these challenges in Technion? Well, I wanted to give you an example of few of the individuals, faculty members that we have in the department that are already working on these challenges. So these are all junior faculty members that truly represent the important diversity that is much needed to address these challenges. So the right kind of diversity that we're discussing here is not based on, of course, all kinds of diversity is important, but is beyond the superficial metrics of diversity. But we are talking about diversity that is scientific. So individuals that came from different schools of thought, from Princeton, from Stanford, from MIT, from Caltech, and they've joined our department because it's a really good place to be and to be able to serve the nation state of Israel. And the problems that they're working on are water desalination, noise suppression, green aviation, and hypersonics, which is really, really nice. So I wanted to give you a very small feel about my own research as well. So I'm the head of the Turbomachinery and Heat Transfer Laboratory in the beautiful jet engine building. This was a building that was donated by the Tark family. And in the lab, we are a body of 30 individuals from 15 different countries. And we conduct research in the field of micro gas turbines for propulsion and power generation applications. So we have, at any given time, around 12 running projects. So among them, I wanted to give you a taste of 3 of them. So one of them is active aviation noise cancellation. You know, as the cities are growing around the airports, aviation noise is becoming an issue. So one of the technologies that we're trying to promote is active noise cancellation by a special speaker that is motionless. It does not move. The only reason that it creates sound is because you can change its temperature by small oscillations. And how is this done? You're all familiar with this. When you plug your old radiation coil heater to the wall, you hear a noise, right? It's buzzing. And this is exactly the same reason why we can actually create noise without any motion, is small temperature oscillations of that coil. So now we're applying that to the basically stationary parts of a jet engine in order to be able to cancel the noise through destructive interference and annihilate it globally. And the basic principles are exactly like the Bose headphones, right? So all it does is it detects the noise that's coming, creates equal in magnitude and opposite in phase noise, and then it gets canceled out. But the difference here is that we are not canceling it localized to the observer, but globally for everyone, because we are doing it at the source. So another project that we're working on is associated with small-scale aviation platforms, drones, right? So drones, as you know, they have a flight time of around half an hour, max. So that's why we don't actually see as many delivery drones and all that, because they can basically just deliver a payload and maybe they can make it back. So the main issue here is the energy efficiency of the batteries. The batteries are not efficient. So the way that we are addressing this challenge is by building the world's smallest micro gas turbine for power generation. And you can actually see some of the samples over there. I brought in some, in my opinion, cool toys. And the breakthrough technology in here is additive manufacturing. We have incorporated additive manufacturing to the design space rather than just using it as another tool of making parts. And you can see how funky looking the rotors and all that are. So the envisioned impact of all this is that delivery drones will have a flight time and payload that will be increased by a factor of 4. So essentially, imagine your drones flying for 2.5, 3 hours with payloads that are much greater than what they can carry right now. So that brings us to the last thing. So during COVID, we were all plagued by the supply chain, and we actually thought that there was really going to be a shortage of ventilators. You know, some of our families got sick, and we were really worried about that. So we know nothing about, in my actually department and also in my lab, anything about medicine or biomedical field and all that. But luckily for us, ventilators, they're just basically small compressors, blowers that can transport air and oxygen to the lungs of a patient. So our challenge was, how can we create ventilators in a fully pre-assembled form and on demand without relying on any other parts? And what we have done is, you can see on the bottom left, a truly unique design of a ventilator that comprises of a turbine, a blower, and a hydrostatic bearing that can actually support the rotor inside the stationary housing. And you can also see some example of that over there. So, and then we transition this technology to jet engines, because once you have a turbine and a compressor and a bearing, the only thing that a jet engine needs beyond that is a combustor, somewhere to burn the fuel, right? And combining that, basically this combustor technology, what you can see here is an engine that is fully 3D printed, pre-assembled in its final form, that's made from nickel alloys, and you can see that engine over there. So the future vision that we're trying to touch here is on-demand manufacturing of parts, absent of a supply chain. So you just go home, and you press play, and you get the part. And as you can see, this is really impactful, especially for military, right, where supply chain is critical. So with all that said, I'll try to sum up in a few words. So our department has a really clear future vision. Besides all these areas, we want to recruit 20 new faculty members in the next decade in order to be able to come up to a number of 32 active faculty members. And in addition to that, in order to be able to address all these challenges, we want to double our undergraduate student body and double our graduate student body, so to 700 and 300 students. And unfortunately, the biggest impediment to fulfilling this vision is our infrastructure that's literally on crutches. So what you can see on the right-hand side are physical, literal crutches that are supporting the historic aerospace engineering building that's basically completely evacuated at the moment. And on the left-hand side, you can see some of the laboratory space that's actually in really awful condition. And this was already identified as the greatest impediment by the International Evaluation Committee that came to supervise our department and its activities. So the future vision to be able to address this need is new infrastructure. So we would like to build a new building of 6 stories that will have classrooms and study halls and new research and also teaching labs. So problem-based learning is a big part of our future vision, as well as office space for collaborative work of the students. And of course, in addition, we will be renovating, hopefully, the historic 70-year-old building and renovate some of the old laboratory space that we have. In summary, for the past 65 years, Technion's Aerospace Engineering Department really leads the national education and research in the field. We have a clear strategic development plan that we put together to expand into emerging research areas that we believe will be the future of aerospace engineering. And in order to address that, we will enlarge the department in size and scope. And in the roadmap for implementing this vision, outdated infrastructure is the #1 obstacle. And with your support, we hope to bring the future into a reality. Thank you.
I want to give you a little grief. Purdue yesterday lost. It was the #1 to number 16. I'm from Chapel Hill, so basketball brackets, okay? Sorry about that.
Yeah, quite unfortunate.
We've heard from Beni, a wonderful experience as a faculty member. We've heard about the need for aerospace modernization of a building in order to recruit people and for the future of Israel. And I think we've heard a little bit about the impact of American dollars to help. You have said that the faculty is probably among the top 10 in the world, but you believe it can be #1. Can you explain?
So the answer for that is actually quite clear. It's not only me saying that. The new faculty members that are coming into our department are saying that. So historically, like me, there were Zionist and passionate Jews that were immigrating to the department and trying to contribute to the state of Israel. But now, we have even non-Jews that are lining up and applying to our department to be faculty members and share our vision in order to make it into a reality. So we are clearly in the world being identified as one of the emerging departments in the field, which is something really amazing, because being the best in Israel as the only aerospace department in Israel is trivial. But the challenge in today's academic environment is to be a true global leader. And with the junior faculty that we have, they are true world-class leaders. We have people that were the best students of all US establishments, European establishments, and we keep growing. And this is something really positive. The momentum is on our side.
Great. I just want to ask a real quick question because I know we're time limit.
Yeah.
I was really thrilled to see, my field is medicine, and I was thrilled to see that you were able to think of things like during the pandemic, how to meld one department into the needs of another department. I know the Technion is really well known for this, but thank you. Okay.
Thank you.
I want to open it up to the public. Questions, please.
Michael Miller. It was touched upon, but obviously one of the problems or one of the issues in aviation today is carbon. And aviation fuel is about 6% of carbon emissions, if I remember correctly. It was touched on a little bit. You mentioned ammonia. Other people have talked about things. What are the fuels that might replace carbon-based fuels, and how close are we to those?
Mm-hmm. So there are, thank you for the question. So there are two separate ways of addressing this issue, which both of them Technion leads. One of them is actually catalysis. You can make fuel that utilizes carbon as a part of it from basically thin air, right? So you can recycle the carbon that has been already out there and turn that into your fuel and continue moving your platforms. So that's approach number one. The approach number two is making new fuels. And when you make new fuels and you make it for sustainability, you need to now remove the carbon from the equation because you don't know where that fuel is coming from, right? You need to ensure that it has no carbon in it. So hydrogen has a lot of buzz all around the world, including Technion. So there's quite a few initiatives, both in terms of the sustainability initiative and the Grand Technion Energy Program, which have done massive contributions to utilizing hydrogen. The problem with utilizing hydrogen in aviation is storage of hydrogen, is not burning of hydrogen. The very first flying jet engine in 1939, which was the engine of Hans van Ohayen, it was a hydrogen burning engine. So we know how to burn hydrogen really well. But the problem is We might know also the Heidelberg incident where the blimp just explodes, right? Hydrogen is explosive. So the main challenge is storage of hydrogen. So because storage of hydrogen is so challenging, the method to approach this problem is to have a carrier of hydrogen, which is ammonia. Ammonia is just nitrogen and hydrogen together, but it's stable, and it's not explosive. So then going through a two-part combustion process, burning process, in the first part, you release the hydrogen from the NH3 molecule, and in the second part, you use the hydrogen that you generated on the spot to burn it. And we believe that this is a much more applicable way of green aviation.
Two brief questions, the first one of which will really expose the depths of my own technological ignorance. The first question is, I have some idea of what fluid mechanics refers to. I have no idea what computational fluid mechanics might be. I'm curious about that. And the second thing is with respect to energy, propulsion, and the environment, is either at your or any other level of Technion, is there much work going on related to fusion power?
Fusion. I'll say a few first about the CFD, computational fluid dynamics or fluid mechanics. So we're actually lucky as aerodynamicists or fluid mechanics people. The equations that describe the fluid flow are fully known. I can actually write it out for you, and these equations dictate exactly how the fluid behaves no matter what. So the physics, we have established it. Now that's the fortunate part. The unfortunate part is that we don't know how to solve them. So these equations are called Navier-Stokes equations. And in order to be able to solve them, what we do is we create models, essentially meta-models in a sense, that don't exactly solve the equation that dictates the physics, but captures most of the physics for the scales that you're interested in. So computational fluid dynamics or fluid mechanics is a field that addresses exactly that. Is how to be able to create models that we can solve in order to address the future applied directions. With all that said, nowadays, direct Navier-Stokes solutions, so DNS, is becoming much more, it's an emerging way of solving problems. But the problem with DNS, direct solution of these Navier-Stokes equations, is you still need to make a lot of assumptions for your solution set to come right. So it's actually really a challenging field. Now, regarding fusion, I personally don't know anyone in our department that's addressing that. Maybe Professor Rizvan can say a few words in the breakout sessions about that. I'm a bit ignorant about fusion.
The investment needed in order to go into fusion is in the billions of dollars range. There is a national attempt which will hopefully fly to go into fusion, experimental fusion facilities, but it is beyond what we can do as a university. Actually, nowhere in the world it's a university, just too expensive.
Okay, I think we're sort of time limited, so I want to first of all thank Beni and say that what the work you're doing is fascinating, and we're very fortunate to be a part of it and hear about it, so thank you again. Bring those dollars in for that beautiful building.
Thank you.